Okay, so a quick talk about this system. I'm, by the way, Domagoj Vrgoč from PUC Chile and Institute for Foundational Research on Data. And I'm going to talk about this system that we've been building that's called MillenniumDB. So let's see, what is this? It's an open source graph database system. So you can download it. And the design philosophy is basically, it comes from the thing that theoreticians and researchers have been telling industry, look, we know how to do this for a long time. And this is how you do it. And then we tried to test this if what pure research was telling is actually true. So we built a system that's based on recent research developments on worst-case optimal algorithms and path queries, and it stores graph databases. So it's an actual system that stores property graphs of this form, as you can see here. The storage is classical, means relational. So we really store it as a relation. To store this type of a thing, you can think of having a relational database with free relations, right? You can have connections that tell you from this node, the from, I can get to this node, the to, with an edge of this type, acts in, and I tell you which edge I'm talking about. Then I can talk about properties of a node. So N1 has a property name and the value is Clint Eastwood, or I can say label of an object, N1 has a label person. There's a bit of redundancy here, but so what? I think Stefan had a question on some talk afterwards. So this actually allows you multi-dimensional-ish data. I gave a talk about this on grades if you want more. So your edge can again be a node. So, edge ID appears here, but later on it can be a node. So you can do this in place reification. Check the grades paper if you want to see more details about that. But if you like to think about it as a relational database, it's a relational database in essence. So it uses traditional relational on-disk storage. It's B+3s, different permutations of all the relations to do path navigation and to do worst-case optimal algorithms. Buffered execution, so you can load Wikidata with 1 terabyte of data on a machine with 4 gigabytes. In principle, this will work if you wait long enough. It supports full pipelined execution, means you can halt your query, pipe the results upwards in any operator, any query you're doing, and continue later. That's why it allows graceful timeouts and interrupts. It has, classical algorithms for joins, like Selinger and greedy left deep plans and worst case optimal. And it has automata guided search for path queries. So of course, since we built this thing, we wanted to know if this is any good. So we did some benchmarking. Sorry, we didn't use the LDVC benchmark, don't be mad at us. So this database was built with Wikidata in mind. I actually wanted to call it Wikigraph, but my co-authors prohibited me from doing so. Anyway, so we did benchmarking on Wikidata. The base benchmark we have, and this is published, I'll leave a resource after, a few of them is Wikidata Truthy version. So this is kind of a smallish copy of Wikidata, maybe 10% of what they have, cleaned up. It's 92 million nodes, 1.25 billion edges, and it's very diverse. So you have 46 million edge types. So it's not, it's a real data set built by the users, very skewed distribution of everything. So yeah. And to query this, if you've seen Wim's talk in Sigmod, in Pods, the tutorial, he said, there are Wikidata query logs available, you can analyze them, but there you have millions and millions of queries. So how do you select something interesting? So we thought we would concentrate on queries that timed out. We extracted 2 main data sets, joint queries and property paths queries. Mostly of these were kind of problematic. And this is what we tested on. I'm going to talk only about path queries. Sorry, I guess you know what this is. I gave you 2 nodes connected by a regular expression, etc. And we did some experiments on our machine, which had a lot of RAM, but only 1 core and 5-minute timeouts. And yeah, I'm going to talk about property paths. So here are the results. Right, so we tried this with your favorite engines and they worked kind of okay. So when you think about it, we thought this is gonna time out all the time, right? And if you play nice with RDF engines and with Neo4j, they do okay. And this is not amazing if you're thinking about high throughput queries where this needs to be answered in, less than half of a second, but it's not so horrible, It kind of works in an order of 2-3 seconds. They all perform similarly. Jenna, which is the reference implementation for RDA, for Sparkle, probably the only one that implements the full standard, is actually the best one in terms of the overall distribution. So these are box plots, first and fourth and third quartile, etc. And these are us. These are our different implementations. They have cryptic names, which you probably know what they are. And they kind of seem to work better, at least in this distribution style view. You can also view it this in, pure metrics, averages and medians and timeouts, etc. So most queries were supported by all the engines. Neo4j doesn't support full property paths, so we had to exclude some queries. But again, these are real queries, so these complicated property paths don't appear in practice that much, so these are user-posted queries. So you didn't get these, things that us theoreticians write to crash the engine. So they kind of worked all right. And if you think that originally these were all reported as a timeout queries, they didn't time out that much. But the averages and medians were much slower than the stuff we had, like much, much slower, up to the order of 20 or so. So the question is, of course, what is going on? What are these super clever and implementations we have? So the way we implemented this is when I started my PhD, I was told by theoreticians, we know how to implement path queries. And this is how you do it. You view your graph as an automaton, you view a regular expression as an automaton, you do the cross product on the fly, and then you do reachability check. And you do this with your favorite graph algorithm, like breadth first search, depth first search, A*, what have you. Let's illustrate how this would work. And let's assume relational storage that we have. So let's say I have a graph of actors in movies, Kevin Bacon acted in this movie, this person as well, etc. Right? So I want to know all the people who have a finite Bacon number. So they co-starred with Kevin Bacon in the same movie or, transitively did so. So this is our syntax. Looks like cipher, sure. So yeah, how would this algorithm work? Well, for your regular expression, you would construct the automaton, which says, this is a start and an end state. You move with an actor edge in reverse and then forward, and then you have an answer. So basically on our graph, this would work as following. Let's say we're talking the breadth first search approach. You start with your start node, the Kevin Bacon one instantiated here, you tag it with the initial state of the automaton. Since this is also an end state, you output it, right? And then you go forward search based on your edge. It says, okay, I'm here in this pair node automaton state. I need to traverse this transition. Okay, so give me all the neighbors reached by actor in reverse from this node, right? This is just a comment of what Peter was mentioning before in another talk, that if you have relational storage, then maybe this is not the best idea. The point is, if you have relational storage, you don't need to bring anything into the engine apart from the neighbors of the current node. And since this is going to be paged, you can just page, you can stop it wherever you want. And the requirement is you have one page of the storage pinned in the buffer, not much more. If it depends on the algorithm. For depth first search, you're going to need the path length, but this is not horrible either. So this is kind of the idea of how this would work. Of course, you have to index different permutations if you want to be able to go in reverse. Like here, you have to have connections in reverse, right? So this is bloat on disk space, but on RAM, it's the same. So the algorithm then works the same, like it's here. With this node, gets actor labeled neighbors, goes there. Since they're all output, you output, and that's how it works. So there is no magic, really. It's a really simple algorithm. We've all done it 1 million times. You're just running it on this product graph. Maybe a bit of what can we return in the engine. So, you know, this is in line with all of these GQL standards, etc. So you don't want to just return endpoint nodes like in Sparkle. This is one huge limitation there, right? So you want to maybe return paths. So we support two things. You can return a single shortest path. This is what the path variable is here, or all shortest paths for each pair of nodes that connecting them. So again, this is I give you nodes N1, node N2. If they're connected by my pattern, like this one, I'm going to return you, yes, they're connected. Plus, I'm going to give you a list of all shortest paths that witness this connection. Just the shortest one. Yeah, also, yeah, one thing I didn't mention, and this is kind of important for the GQL crowd now, you guys here as well. What type of path am I talking about? So I'm talking about walks here. So anything can be repeated, anything you wish. If you go into trail and simple, then it's a bit more tricky. We don't support this yet. So it's just arbitrary path semantics. All right, that's what I just said. I can't go into this, right? But I just wanted to show you, if you go into pseudocode of how this would work, this is really just your classical search algorithm. Like if you swap this thing for for a stack instead of a queue, you get depth first search, so nothing weird. You initialize your stuff, you have your search frontier, you have your bookkeeping set that tells you whose predecessor and what you visited so far, and then you do this picture that I was showing. You start with the start node with the automaton state, no predecessors, then you pop, you see if you're in the end state, you return, and if not, then you go forward. When you actually implement this with B+3s, you can do early detection of answers, not when you pop from the queue, but this is much more nastier to look. This is just the thing about all shortest paths. So this is kind of a twist on the breadth first search algorithm. It's not very deep what you do. It's basically an observation that if I'm interested in all shortest paths between a pair of nodes, this is the same as running normal breadth first search, just beefing up this bookkeeping structure a bit and remembering more stuff. Again, I would need to give a full talk on this. I just included this if someone wants to check it out. Sorry. A few more comments on paths. So how did we actually return paths? So we return them as a list of node edge pairs. And if you've been to Vimstock, actually what happens in these algorithms that I see here is you build this structure that he talked about. So you have a compressed representation of all the paths. If you want to materialize them one by one, yeah, then it can get a bit bigger. Of course, we're not done. This kind of is a very basic baseline implementation, runs an order of magnitude faster than what engines do. I usually get told that they actually do this thing. So yeah, I don't know what's going on, but we're far from done with this. So this can be like extended in a lot of direction. One is the start in the middle approach, where you can filter, edges that have maybe just one instance of some label. There's only one edge, then you know that you can split your query, go forwards, go backwards, and then see what you get there, which also opens up a space to do parallel executions, which I don't know much that's being done. So this has been something interesting to see. We are still missing trail and simple path support. So this is, yeah, going there. And then the data comparisons along paths. So this is something that we already support, but we don't know how to write queries, basically. We know how to start with an automaton model that allows you to evaluate things, but we don't know how to write them syntactically for the user yet. So this is something that's being worked on. More details, you can get the source code. You can get the explanation of these path algorithms in an archive paper if you want to read about it. And if you want to repeat our benchmarks, I leave two resources. The first one is a bit more raw. It just has joins and path queries, and the other one then has finer classification with the information how to download data, etc. If you actually want to repeat our benchmarks, then maybe write directly to me just to give you a newer version of the code that slashes loading time, like by a factor of 10 or 20. So, okay, just to finish, so maybe you're thinking that this is dumb, that we're redoing this. Okay, sure, it's an order of magnitude faster, but kind of Sparkle engines already know how to use do these queries. So I think there is, in the implementations that exist, there is a bit of a disconnect that people don't understand what's the semantics probably of the queries. So here I have my Kevin Bacon query with a limit 1. And if you run this on the Wikidata endpoint, this is gonna time out. You can try it. I don't wanna do it now, right? Then we're supposed to know how to do this. And my point is, like, there is probably something missing with the way this is implemented, because this by default has one answer, which is this thing here, because there is a star. So there is this thing, but then you were gonna think, okay, maybe they're doing some weird computation, so they don't know how to repeat joins, and this gets very big. So here is an instance of this query that asks for a path of length 4. Well, 2, you go for one movie, another actor, another movie, another actor. And this executes almost instantly. Okay, I mean, not instantly, but it gives you like 830,000 results very fast. So they know how to do this by joins. It's just there is some disconnect in the way that actual property path queries are implemented. So my message here is that, this is probably the baseline that anyone would think about it. And I think it's important that we implement it well. So this is what we try to do here. And I think maybe some lessons can be learned from these experiments and implementations. So yeah, thank you very much. Sorry for going a bit longer. Yeah.
No problem, thanks.
Questions?
Questions. I see 2 online. Dominic, go ahead.
Or maybe clarification. You showed the chart with databases, right? And you mentioned
Yeah.
Apache Gina here, right?
Yes.
So my question is, what actually Gina are you tested here? This is a standard Gina or Gina Fuseki, the Spark server?
It's Fuseki.
Okay, right. Thanks.
Okay, everyone also had his hand up.
Yeah, maybe first a quick comment about the Wikidata query service. Might not be the best example, since it's kind of based on an outdated system that they are now trying to replace. So it's not necessarily reflective of how property paths work in general. But my question is, did you look at just path queries with a fixed start point? Or did you also have some queries where the start node might be another?
Yeah. So these are all assuming a fixed start point. Okay, basically. We actually did the experiments of no start point, and we did the most stupid algorithm that we just tried them one by one. Usually you would have some filter, and because this is inside of an engine, so usually you can filter out the starting or ending points somehow, by other parts of the join, and then we just try them one by one. So again, this is not very smart, but it works. So actually, like something that was presented earlier would work much better in this case, like this, doing multiple at a time. It has much higher memory footprint, but in terms of time, it saves a lot. So yeah.
And did you say that the data set is also available? There's a link there?
Yeah. There is a link. You can download it. It's Wikidata Truthy dataset. We just tell you how you can load it into our engine or into Neo4j.
Yeah, last time I checked, Wikidata Truthy was like 6.5 billion. So yours seems to be smaller.
No. But this is the Truthy one. I think you're thinking about the full version.
No, full version is like 17 billion. It's okay. I'll
okay, yeah, you can check it out. Yeah.
Thank you.
I also could ask a question. Thanks, Domagoj, for the interesting presentation and first signs of life for me, at least, with regards to MillenniumDB. So welcome to the family of systems architects. Hey, this benchmark, actually, this slide. Okay, you benchmarked against these Sparkle systems.
Mm-hmm.
All systems they are not exactly known for their very high performance. So.
Mm-hmm.
despite that you think that that your result is orders of magnitude bigger, then yeah, if you would have tried Umbra, maybe the picture would have looked different. In any case, a small tiny remark before my real question comes is that Virtuoso, even though it's no longer maintained for a long time, it had actually an extension to do pathfinding that not many people know about, but so it doesn't look really beautiful, but there is a pathfinding algorithm in Virtuoso. Did you use that?
No, I have no idea about that, to be honest. Yeah.
No, it's okay. But the real question. So you said, and actually that's what I also heard, that the common thinking among theorists is, or the like even trivial knowledge, that in order to resolve path query, you make this cross product of the query and the graph. It's fascinating thought, and also to do that, and then you get the best kind of complexity. Hey, but that's not what you did here, is it?
Yeah, that's it. It's just like this product, this is also what you're taught in theoretical approach. You don't actually build it, you build it locally. Like you just are, you have your automaton, which is tiny, your graph, which is huge. You start exploration in some node of the graph, and then you're building this thing dynamically as you're exploring the graph. So this is what's going on.
Indeed, that was my point. Your query was clearly an automaton, but your graph was not. So what are you actually doing on the fly then? What can you illustrate this slide where you're?
Yeah. Look, so it's basically like this. What you build is a pair node of the graph automaton state, right?
Yeah.
Okay, and then I started here, and then you go forward. Yeah. You're here, and then you scan your automaton, and you look. Okay, so there is this edge that goes out, this transition in the automaton, right? Can go from actor to a movie, going on actor labeled edge in reverse. Okay, so basically what I am saying now in the algorithm, okay, go to the B+3 from Kevin Bacon with an actor in reverse, and now give me the neighbors. And then I know, okay, this thing in the product graph corresponds to Footloose with Q-movie, this with another movie with Q-movie, etc. So this is what because this thing that you're building, this is part of the product graph, actually.
Yeah, but I see an automaton there. I see.
No. Okay. Yeah. This is just like an idealized thing. You can see think
the product of your automata.
So
like
the query automaton, but the graph, you can think of an automata in a sense. You have nodes which are states, and then the labeled edge, which is the transition. That's the intuition.
Oh, okay. Well, but then that's a no.
Yeah, I guess.
Okay, yeah, there is yet one veil of mystery has been taken off. Okay.
Yeah, I think this needs to be written down in a bit more detail so that everyone can.
That is, this is not what the cross product of. Okay.
Yeah, I agree with you.
Beautiful mathematical phrasing, but the emperor has little clothes.
Yeah, fair enough. I agree with this. That's why we had to implement it, right, so that someone would listen.
Okay. Can I make a quick comment?
Sure.
Yeah. Okay, so recently in the recent years, you have most of the triple stores, most of the Sparko engines implementing pathfinding extensions. So I encourage you to try those and to measure those, because obviously if you try vanilla Sparko, it's gonna be what you're getting. But then yeah, Stardock has it, and from Montex GraphDB has it. So yeah, I encourage you to just give it a try, because there is a lot of work done. So it will be curious to see how it feels to you. And yeah, if you don't want to load Wikidata Truthy in GraphDB, we have an access point that we can share with you so that you can extend your research.
All right, cool. Sounds very good. Thank you.